guys, so welcome to the video, and in this video I'll be solving this problem on dimensional analysis. So the question is saying that the radius of a circle that is inscribed in any triangle whose sides are ABC is given by the formula that you can see here. Okay, and they've said that where S is equal to a plus b plus c over 2. Okay, now they want us to prove that the equation is dimensionally correct. Okay, so now if you're in my tutorial group, I'm pretty sure you know that I'm not the kind of a person who just rush directly into solving questions. I like beginning from the basics because the basics are very important. That's where the whole topic depends on, and there is a concept that I'll explain on the basics that you need to be familiar with to solve these kind of questions. Okay, and that concept, it is rarely taught. Most of the tutors and lectures don't teach it. Okay, yeah, some talk about it, but they don't explain it in depth. Okay, they don't explain it with examples. But I'll try my whole level best to make you understand the concept that I want you to apply on this question. And it's a very simple concept once you just come to know about it. Okay, it's just that you don't get exposed to questions that involves the concept that I'm talking about. Okay, so without any further ado, let me rush to the basics. Okay, so let's look at the prerequisites. There's what I call the prerequisites, or in other terms, you can say the basics. So prerequisites are simply some concepts or some terminologies that you need to be familiar with before you learn something. In our case, before we learn how to solve such kind of questions. Okay, but even though I've taught the whole topic in my tutorial group, but I'll just summarize them up for you all, in case maybe, because I'm pretty sure there's somebody with maybe zero knowledge on dimensional analysis, or maybe with little knowledge and they want to know how to solve that question. So I think I'll just do a very quick rewind to the basics. Okay, so dimensional analysis, I'm pretty sure you know what is very important. So you need to know that we deal with three dimensions which includes the length, the time, and the mass. Okay, these three dimensions are very important, are the ones that we're going to be dealing with. If you're in my tutorial group, I'm pretty sure you know the mnemonic that I showed. If you're struggling to remember these three, you can use the mnemonic that says that take my laptop. Okay, you can use this mnemonic to remember the three dimensions, where T is representing time, M is representing the mass, L is representing the length. Okay, so the way that we use these dimensions is that let's say in a question you'll be given quantities. Okay, so you replace the quantity, or you substitute the quantity with its dimensions, and the way that you do is that, let's say for instance you've been given velocity. Okay, velocity. So the dimensions are derived from the SI unit of the quantity that you're dealing with. So it's very important to be able to recall the SI unit, because once you're able to recall the SI unit, then you can easily come up with this dimension. And I showed that the easiest way to come up with the SI unit is to use the formula. In case you're struggling to remember the SI unit, you can just derive the SI unit, then you convert to dimensional form. For instance, velocity. You know that velocity, it is a displacement over time. Okay, so you know that displacement is measured in meters, right? And then time is measured in seconds. So you can easily write it like this. You can take this SA. This S seconds is having the exponent of 1. You can easily take it there on the numerator part, and you are going to have meters with the seconds raised to the power of -1. Okay, even acceleration, but okay, the key is to just be able to remember the SI unit. Even acceleration, you know that acceleration is measured with this SI unit, s squared. Okay, so you can easily take this there on the top, meaning that you're going to have meters with seconds raised to the power -2. When it goes on top, the sign changes. If it is negative, it will be positive. If it was positive, it will be negative. So now after you come up with the SI unit, now you're going to replace with the dimensions. M is representing meters in this SI unit here, right? You know that meters are used to measure the length, so meaning that where these meters you put the L dimension representing the length, okay? And S is used to measure the time, right? So you're going to get to check on the dimensions that we used. You're going to check which dimensions are used when you are measuring the. You're going to ask yourself with the time when we use the second. We use the seconds when you're measuring the time, right? So here you're going to put t raised to the power neg 1. Even here you're going to check the meters. You're going to put the L, the length there, and then where this S representing the seconds falls under the dimension of time, right? So you're going to put the TA in raised to the power neg 2. So these are the dimensions that we are going to be interested into, okay? These are the dimensions. These are the dimensions. There's a difference. These are the SI units, okay? The SI unit of a quantity, and these are the dimensions of the SI unit. So now, on dimensional analysis, you need to normalize using the dimensions, okay? When you're solving the questions, I've seen some students, instead of using the dimensions, they use the SI unit, but you should normalize using the dimensions. This is why it is called dimensional analysis. They want you to apply these concepts. The lecturer want to see if you're able to notice which one is falling under the dimension of time or mass. Okay, they want you to see this. This is the standard way. You need to be using the dimensions. Okay, so I know I might be rushing right now because this is just like a summary. So the key is just to know the SI unit of a quantity that you're dealing with. So now let's pass that, and then now let's look at the dimensional. When they say something is dimensionally correct, what does it mean? Okay, so now let's look at what it means if they say. Now let me just what it means if they say that an equation or a formula is dimensionally correct. So you know that a formula is made up of the quantities. For instance, your force is equal to mass times acceleration. This is a quantity, this is a quantity, this is a quantity. Okay, so now remember that every quantity that has SI unit, it should also have the dimensions, because the dimensions are coming from the SI unit. So now when they say that something is dimensionally correct, they mean that if you were to leave this in its simplest dimensional form, and these the quantities that are on this side in their simplest dimensional form, you're going to end up with both sides having same dimensions, meaning that if you were to simplify this, you should at least end up with maybe I'm just giving an example. Maybe the left hand side should have L, the length dimension, and the right hand side should have also the length dimension. If you end up with something else, maybe let's say this side is having L like this and the other side is having maybe T, after you simplify them, then it will mean that it is not dimensionally correct. So the dimensions on the left hand side and on the right hand side should be the same. And one more thing, let's say a case maybe where like you have, let's say, LA, okay, and here you have also L, but this time it is raised maybe to the power of 2. This is still not dimensionally correct, because it's same as having maybe it is same as having like this, okay. So even the exponents should be the same, okay? The exponents should be the same. It can only be considered dimensionally correct if the dimensions and the exponents that they are having are the same, okay? So this is the common explanation that almost everybody teach. Now there is something that they don't teach you. Yes, there is something, I think, okay, let me just explain it to you. So there is something that they don't teach on this concept of knowing whether something is dimensionally correct. Okay, so there is another thing that you should consider before you conclude whether something is either dimensionally correct or not. And this is that for an equation that is dimensionally correct, the quantities that are adding should have the same dimensions. What do I mean by that? I'll just give a random formula. Imagine maybe a formula like A is equal to B plus C. Okay. Imagine you have a formula that is involving somewhere where there is a plus or minus. Okay, and I know I've just said adding. It can be addition or subtracting. So if you have a formula where you are having some some quantities that are either adding or subtracting. For it to be considered to be dimensionally correct, it will mean that these quantities are the same. Okay, so mean that if this one is having the dimension of length, even this one should also have the dimension of what? Of length. If this one is having some other dimension, or maybe if it is having like length squared or maybe length with the TA, it is not. They cannot be added or subtracted if they are having different dimensions. So every time you see an equation where maybe there is like, okay, this plus this, as long as there's plus or minus in the equation, just know that these, if you were to simplify them in their simplest form, we are going to end up with these two quantities that are either adding or subtracting having the same dimensions. I think that can easily be understood with an example. Let me give you a very quick example on a very common, I think on two common equations that if you remember, maybe in high school, maybe you used them, and even here, maybe in kinematics, you'll be using them. So let's look at these two equations. So there is this equation on linear motion or kinematics, which is v is equal to final velocity is equal to initial velocity plus acceleration times time. This equation is found on kinematics. I don't mean that you have to know it on dimensional analysis. You don't need to master equations on this topic. You just need to know the SI units. Okay. So this question is very common. This equation is very common, and it has been used. The formula, this formula has been used for many years. Okay, it's there in every book. And one thing that you should know is that for a formula to be considered that no, this formula is able to give correct answers, it means that it is dimensionally correct. If it is not, then that formula can't even be put in any book. Okay, so every formula that you have ever been using in physics or even chemistry, just know that the scientists had to prove that it was dimensionally correct by applying the principles that I'm teaching you right now. Okay, so even this formula is dimensionally correct. Yes, it is. It gives correct answers. You've been using them and you will be using it. Okay. So now, how do you prove that this is dimensionally correct? So remember, I told you that you need to recall the SI units. You know that the SI unit, this is velocity. Whether the velocity is initial or final, it will still have the SI unit of meters per second, like this. Okay, you know that acceleration has got the SI unit of meters second. The negative just showing that it is on the denominator. I've just taken it there on the numerator, and t has got the dimension, which is the units, that is the seconds, right? So now in their dimensional form, this is meters falling under which one? The length, right? The s seconds under the dimension of time, right? Raised to the power negative. Okay, and then the acceleration. This is meters. It is falling under the dimension of the length, right? And s under the dimension of time, right? And raised to the power -2. Okay, and then the t time seconds under the dimension of time, right? So now let us replace or substitute the quantities with their dimensions. I show you that you're going to end up with the sides having the same dimensions, and you're also going to end up with, you're going to find that these two are having the same dimensions, and I'm going to show you right now. Okay, because you need to know this concept. If you don't know this, you're not eligible to solve that question that I just showed you. It's better you just even stop watching this video or rewind. Okay, make sure you rewind, because this is what you need. If you don't know that question, then you won't understand anything. Nothing will make sense to you. Okay, so let's replace where there is v. I'll put L T like this. Even this I'll still put, because it's still the velocity. It's just that it is initial velocity. So you're going to say t. Okay, and you're going to say plus a, and where there is acceleration, you're going to say lt. Okay, so you have acceleration being multiplied. Here it's like there's a times a. Okay, there's like a times the dimension for time, which is t. Okay, so let me just now expand this. So you're going to say here, I'll just write the way they are. I'll say LT plus. So here's like you have them like this. Okay, this is raised to the power of 1. Okay, in case you can see. So we can also write them like this. Okay, I've just replaced the quantities with their dimensions. Nothing serious here. Let me just quickly write this on another page. Okay, so this is what we're going to get if we replace the dimensions. So you're going now to simplify the dimensions. Okay, as you can see here, there's the dimension for t multiplying the dimension for t. There's a concept in mathematics that if two equal bases are multiplying, you add the exponent. For instance, if you have a to the power 2 times a to the power 2, the answer should be, first you write the base that is in common, which is a, then you add the exponent 2 plus 2, that will give you 4. This is how you solve these calculations. But don't worry, you don't need to understand this in depth. You just need to know how to apply this concept a. So you are going to say that neg 2 plus 1, these are like multiplying. Okay, these are like multiplying. So here you are going to get a t. This is positive 1a, this is negative 2. Yeah, so we are going to say neg 2 plus 1. It will give you neg 1, right? It will give you negative 1 there. So, meaning that you're just going to write LT neg 1 is equal to LT raised to the power neg 1 plus. So, here you're going to just write 1t because you have already done this, what I just did here. You only write one base, not write the two of them again, because this time you like join them. Okay, so you're just going to write t raised to the power. Now, as you can see, we have what? Same dimensions are adding. Okay, so now, remember, and I mentioned that now for us to say that now it is even dimensionally correct, this side should be equal to this side. Okay, so now there's another concept that if the two dimensions that are adding are the same, it is same as just having one dimension. Okay, it is just same as this side. It is like you just have it is like you just have, I mean, it is just like there is just one dimension on this side. Okay, now let me not show you the shortcut. So here what they do is like they consider this as the like terms. Okay, they are like terms, and imagine these are like terms, so they can easily be added. Okay, and when they get added, they form one thing. The same way you do like a squared plus a squared, you're going to get what? 2a squared. So even here, that's what is done. So you're going to say LT like 1 is equal to yes, like there is 1 here in front, so it's like 1 plus 1, that will be 2. Okay, now there's something again that I'm about to explain in case you don't want to apply the shortcut. So here you're going to say the power. Okay, when you add these are like, if you want to okay, if you maybe if this is confusing, you can just say, okay, now let LT raised to the power neg 1 be equal to like a. Then you put here, you put a and a. You're going to find that a plus a will give you 2a. Then you come and replace it back. Now you can just consider them to be like terms. Then you add them. You will also add whatever is in front a. Okay, if it is able to be added. Okay, so now after you do that, you're going to end up with this. So now, as you can see, we have the dimensions that are the same. Now, I know some of you get confused. I've seen some students whereby somebody maybe reaches a point where maybe he have on the left hand side, maybe he has the length. Okay, on the right hand side, he has the length, but here there's maybe like a k here. And you'll be like, no, sir, on this side, yes, there is a length dimension. On this side, there is another length dimension. Now, since here there is k, meaning that it is not no. You only consider the dimensions. Ignore the constant. When you're determining whether something is dimensionally correct or wrong, you only focus on what? On the dimensions. No wonder they say dimensionally correct. There is a word dimensionally. They want you to focus, put your eyes on the dimension, not on the constant. Okay, they would have been adding the word constant. I'm just trying to make things make sense. Yeah, but your eyes should be on the dimensions. You know, lectures can be very funny sometimes. In one question, they instead of putting where I've put 2, they had put maybe a cos, like cos, maybe cos theta. You know that cos theta doesn't have a dimension. This 2 is just a number. It is a constant. Anything that does not have dimensions, it is considered to be a constant. It is a dimensionless um, constant. Okay, so you only focus on the dimension. So by just reaching here, you can see that here we have one length, one time dimension raised to the power negative 1, even a one time dimension raised to the power negative 1. So you have a dimension. You have proved that they are dimensionally correct. Okay. Now, yes, some people just use the shortcut, but I've seen lectures marking both methods. But I think this is a very easy to understand. But some people just replace. They just say, oh, okay, since they are the same, they just write this. They just write it again. They ignore this. But lectures want to see you having the same dimensions. But I think you should just be using the one that I've just showed you. Of course, them to be the like names. Okay. So this is how you show. Okay. So you focus on the what, on the dimensions, ignore the constant. So this is what you need to know. So the moment so let's say here when I added, maybe let's say here maybe I'd like the dimension for m, I wouldn't have even proceeded going any further. I would have just ended here and concluded that this is not dimensionally correct. Okay, so you need to know that. So there's another case. Let me just not talk about that. But in most of the equations, most of the questions, they don't really add. They just write it again on this stage. I'm telling you this because you'll be seeing some solutions where they don't add them like the way I have. Okay, they don't add them like the way I have. Maybe they'll just instead of including the 2, they just write it because the moment they just see that same dimensions are being added, they just write the only one dimension instead of adding. But even if you do, you still get the same answers. The constant won't affect the final answers. So, but in the way I've solved that question, I'm not going to be adding them like this. I've only done this for, I think, explanation purposes. If you want, you can do. It won't affect your final answer, but I won't be doing this. Okay, you'll still be marked. They'll still mark you. Actually, this shortcut method is what is commonly used. Okay, this one of just replacing with what is common. So let's, I think, write the question. And I repeat, if you haven't understood it, it's better you even just text me. I explain maybe to you through a voice note or something, but because you won't understand anything that I'll be solving. Okay, you won't be understanding anything. So if you haven't understood this thing, you are now eligible. I think you should even now continue watching this video as I'll now start solving that question. So now I've gone back to the question. I'll read it again. So the question is saying that the radius of the circle inscribed in a triangle whose sides are a, b, c is given by s minus a. The equation, as you can see, where s is equal to a plus bc, blah blah blah. And then they are said now they want us to prove that. Okay, first let's analyze the question. Let us analyze it. Okay, they are saying that there is a circle inscribed. What do they mean, inscribed, or a triangle? You all know that a triangle looks like this, right? A triangle, I know it might not be neat, but it looks like something like this. Now, when they say that there is a circle that has been inscribed in it, they mean that they'll just put a circle and then they place it inside the triangle. That is to inscribe. When you inscribe a circle or something into something, it's like you know what I'm talking about. So they are saying that they have inscribed, they have put a circle inside a triangle. I don't mean that you need to know how to analyze the questions. I'm just explaining this for it to make sense. You don't need to show this to your lecturer. No, just for explanation purposes. I want you to understand. Okay, so they are saying that the circle that has been inscribed in a triangle, it is having a radius. Radius is from ear to ear, right? This is the radius. And now they're saying that this triangle, as you can see, the triangle has got 3 sides, right? There's this side, and this side. So meaning that there is a side that is being represented by A, okay? The other one by B, the other one by C, okay? If you want, you can put B here, as long as you've allocated each side with a letter of these letters that have been given here, okay? So now, Remember that on dimensional analysis, we deal with the quantities. So here, what they want you to apply, they want you to just think, they want you to use your brain, they want you to think, okay. So as you can see, this side, this whole length A is being represented by B, and this whole length A is being represented by A. Even this whole length A is being represented by C. Okay, so it's like C is representing the length. Okay, no matter what we can use to measure, you are still going to obtain the length. There's no way you're going to obtain the density when you measure from A to A. No. Okay, so these are representing the lengths. So if we were to write them in their dimensions, you know that if we measure it, you're going to record it in meters, right? Meaning that the dimension will be of what? Length. Okay, even B, you're going to measure it in meters. This side, it is in meters, not in the decimeter cubic. No, it's not the volume. And you're still going to have the dimension of what? Length. Meters falls under the dimension of what? Length. Okay, even A, meters, still going to be of this dimension. Okay, so you've analyzed some of the quantities. When you look at the equation, in the question, they have only given us how many? 1, 2, 3, three quantities, and what else? Even the radius of the circle. Okay, and the radius is the one that they're representing by the r that you can see. It's the one that we're finding. It's the honor of this the formula for the radius. So you know that radius is from F to A, right? So if you had to measure from A to A, in which unit can you record it? These are the questions you should be asking yourself to come up with a dimension, in case maybe you're in a situation, maybe you're trying to get stuck. So you know that the radius is the distance from the center of the circle to the, I don't know if it's the circumference or something. So now, you know that if you're to measure from A to A, you can't measure in kg, no. It will be in meters. So radius is going to be measured in meters. So you're going to put LA. So meaning that the dimension is going to be length. Okay? So right now you're familiar with the dimension for this, and the AB and the ABC up to R. You don't know the S. So S, you don't know it, but they have given you that S is equal to this whole thing here. Okay. Now, how do you handle this one? So this is where I say that the concept that I taught you, the most of the tutors, even me, I used to attend tutorials, lectures. They never taught me this, especially the way that I'm explaining. I had to study on my own. I had to study broadly. I had to read different books, solve different questions to just come to understand this. So now you know that okay, S is equal to A plus B. I think let me just write it A somewhere. A. So you're going to say S is equal to. Now, you know that A is being represented by this dimension. In dimensional analysis, that's why it's called dimensional analysis. You replace with the dimensions, not the SI unit. That's the standard way of approaching, of solving. And you should normalize wrapping the dimensions in the square brackets. I think this is the standard way of representing them. But if you want, you can just write the dimension. It depends with the lecture, but this is the general, standard way of representing the dimension in the calculations. So you know that A is represented by this dimension. You're going to put LA, okay, plus even A. You know that even it is having L. Even A is L over what? Over 2. When you look at the numerator A, same dimensions have been added. Okay, meaning that if you want, you can apply that of 3. Now that one is going to make your final answer look something else. Okay, but I think the standard way of you just write one L. Okay, because you know that if you were to add L, these are like terms, you're going to get what? 3L. Okay, 3 with this. Okay, you are still going to end up, now we are only interested in the dimension, so meaning that you are still going to end up with one dimension if you were to add these like dimensions. So S would be equal to it's going to be equal to L over 2. This 2 we can't ignore it, but if you want, you can ignore it. Okay, let's just not ignore it. But these constants, these are constants, remember, they don't even matter at all. Whether you ignore it or not, you're still going to get the same answers. Okay, so let me just consider it since it is there in the question. But here you should normalize not considering the constants. That's how they handle questions. Like I've seen from different books, these questions being solved like this. That's what I'm saying. Okay, so you're going to say else. So they are the same. It is same as having just the LA. So you know that S, if you want, you can even write this as S is equal to 1 over 2. I mean 1 over 2, you can split it. You just end with a single length dimension. Okay, like this. So I think let me just write this quickly on a different page. So for now, we've just figured out that S is equal to 1 over 2 with the length A. Okay, let me just write it. Okay, so this is the equation that we've been given, and we just found what our S is. Okay, so let's proceed. So now you're going to replace wherever there is S with your LA. Okay, wherever there is S with the L. Okay, so meaning that you're going to have R being equal to R being equal to, where this S, you're going to say 1 over 2 A is supposed to be A 1 over 2 LA. Okay, minus you know that the A, we found its dimension, it is length. Okay, and then you do the same A. You're going to have 1 over 2 the dimension for L minus here is still have the same dimension. I think let me just put this A. They're still multiplying, so even there you're going to say 1 over 2 the dimension for L minus here there is just L over 1 over 2 the dimension for L. Okay, like this. So now as you can see, this is why the constants are ignored, because they're really going to affect us. Okay, so now here you should ignore the constants. Let me even raise this to power 1 over 2. I don't mean that if you consider them you're going to get a different answer. No, if you want you can consider them, but just ignore them. They are only interested in the dimensions. Okay, if you have enough time, you can consider them. Here you can go on and subtract. Okay, but in this video I will just ignore them. Okay, we ignore the constants, because we are only interested in the dimensions being equal. Okay, the constants don't affect anything except for this the exponent. The exponent we are going to consider it, but for the constants that are coming in front of the dimensions, you just ignore them. You ignore them for only when you are trying to on dimensional analysis. I don't mean that in every question that you're ever going to solve you should be ignoring the constants. No, we ignore the constants because they don't affect the final answer. They don't. It doesn't mean that now if you ignore them, if it was supposed to come out as dimensionally correct, it might come out as dimensionally wrong. No, okay. It will still come out as dimensionally correct if it is supposed to. Okay. Because here it means that you're going to get negative 1 over 2 L, negative 1 over 2. Now that will just make your work very hard. Even the lecturers are only interested in seeing you showing them that the dimensions are the same. You are still going to be marked. Lecturers knows these stuffs. Even in the other books, they get ignored in cases like this. Okay, so you're going to just ignore them. So you mean that here where there is the length dimension. Remember I said that for dimensions to be subtracted or added, it means that they are the same. So this one is already showing us the signs that it is dimensionally correct. Okay, so here in this parenthesis here, you can see that you're just going to end up with what? With just one length dimension. So let me just rewrite this formula. So I'm going to say R is equal to. So as you can see, here you're going to end up with, if you want, you can say 1 over 2 minus 1. You're going to end up with negative 1 over 2. Okay, 1 over 2 with the dimension of L in front. Now, since the constants are getting ignored, mean that in this, when you simplify what is inside the parentheses, this you're still going to end up with whatever the constant will be, but the dimension is going to be what? It is going to be of length. Even if you don't understand this, you can just rewind the video. I've explained what is going on here. So you go on in the next parenthesis, you're going to see that, okay, even if I do if I do 1 over 2 minus 1, I'm still going to get a certain constant in front with a dimension of L. Since we are only interested in the dimensions, you just write the dimensions. Okay, even here you do the same. You're just going to consider the dimensions. Okay, over 1 over 2. Remember, we are ignoring the dimensions because we don't, I mean the constants, because we don't need them. We are not interested. We are interested in the dimensions. Remember, I said that. That's why they have said dimensionally correct. They want you to put the eyes on the dimensions. That's what they want to see. So here you're just going to put the dimension for just L. Don't forget the exponent. There's an exponent, 1 over 2. This one you don't ignore it. Only what is in front of the dimension. You can ignore that one. If in a case where you are proving if something is dimensionally correct or wrong. That's why they just like putting K. They don't want to make things complicated for you. So here you have R equal to. You know that if you want to, where they are putting R, you can just put the dimension for L, but I think I'll just do that at the end. It still won't affect the final answer. So you know that there is a length dimension, the same basis. Here it's like this, power 1, here, power 1. These are like multiplying, okay? They are like multiplying. And I said that if the equal bases are multiplying, these are the same bases, you add the exponent. So you're going to write the exponent that is in common, that is the L, right? I mean the base that is in common, that is the length base, and then you add the exponent. 1 plus 1 plus 1, that will be 3. If you want, you can apply the same mathematical of L times L times L. It is L cubic. This is where it comes from. When you do this in mathematics, when you do that, x times x times x, you get x squared. Behind the scenes, that's what happens. Bases are the same. Here it's like this, power 1. You add the powers to, you write the base that is in common, the x, you even get the x squared. If you want, you can apply this. This is what we're applying in case you're getting confused. Okay, it isn't something that is new. And here you're going to say over L. Okay, now you know that if you want, you can just directly cancel. You can just cancel this. If you cancel this into this, you're going to end up with just the length dimension squared. Or if you want, you can take this on the numerator. Meaning that if here it is positive 1, if it goes on the numerator, it is going to have negative 1. And if you are multiplying equal bases, you write the base that is in common, you add the numerator will be 3 minus 1, that will give you 2. Either ways, you're going to get the same answers. I'm showing you both ways because you'll be seeing in some books they'll do this, in some other books they just cancel. Okay, so I want you to understand that how to do this in all the dimensions, in all the aspects, in all the angles, so that you don't ever get stuck. So here you're going to now end up with the length dimension raised to the power squared. Don't forget this. Remember, we have this. We have the 1 over 2. Okay, so let me just write this properly. So we have radius being I think this time let me just put it in parentheses. So I'm going to have the length dimension squared. Okay, 1 over 2. Okay, now I think this time let me just write this now in its dimension. If you want, you can write it in its dimension maybe from the beginning, but the answer is still going to be the same. So radius, we found its dimension that it is length, right? So here you have, I'm pretty sure if you are smart enough, you even know how this question is going to end. You even know what I'm about to do right now. Okay, so now look what we have. We can't say this is dimensionally correct right now, okay? Because we can just end A. we need to have something that is very. Look at the exponents. The exponents are not the same. Here there is an exponent of y. Here, look at the exponent that we have. We need to simplify this exponent. Okay, so there are two ways in which you can do it. If you want, you can just directly go and since there is this exponent a, which is 1 over 2, and inside a there is a dimension with the exponent of a, so you can now just multiply the exponent, meaning that you multiply 2 times 1 over 2. That will give you, it's like you have 2 over 2, right? If you multiply 2 times 1, you're going to have 2 over 2. That will give you what? 1. So meaning that here you're going to end up with what? Here you're going to end up with length is equal to, with power 1a, meaning that you're going to end up with length power 1. Even if there's power 1, you have proved. Okay, and another way is that maybe in some books, maybe people have different methods. I'm showing you the other method because in case you find that it has been used, you don't get confused. Like okay, now how come? Okay, but Joseph taught me that I have to multiply this. You people are very funny. Just because you find it, you find a different method that has been used. Now you get confused. You need to know that in mathematics or physics, there are different ways of solving a problem. So the best thing you should do is that if you find a different method, you should try to learn that other method instead of you start now contradicting. Now I think this is the wrong method. The one that I learned is the correct one. No. Okay. So here, maybe on this side, let me just rewrite it here, where we add length, dimension for length being raised to squared being raised to 1 over 2. You know that the square root it is same as having anything that is, let's say, x square root. It is same as having x 1 over 2. You know that, right? So what you can do is that you can just write what you have here in the parentheses and wrap it in the square root, put it under a square root. So you are going to have x squared. Okay, you know that the square root, if a square root is having what is under it being raised to the power of 2, it can easily be cancelled, right? They can be cancelled like this. Okay, usually you can find someone that has solved the problem like this. They just cancel and remain with what is under the root. They even remain with x. So even if the same thing can happen, whereby they just get okay. So now they put it now under a root. They'll say okay, like this, and then now we just cancel them directly like this because they know how it works, and they just end up with now what is under the root without the exponent, or with just the exponent of 1, like this. They even write like this, still the same. It is just that this method is very easy to understand. Okay, I didn't want to complicate things by adding. I know some people are just allergic. The moment they just see square roots, they just see the radicals, they even get confused that now what is this? So we have showed, and this is how you do it. If you haven't understood, just rewind the video and watch it over and over again. I don't even know how I've shared this here in public, like this content are supposed to be in my tutorial groups. But yeah, if you haven't understood dimensional analysis, I have videos on dimensional analysis in my tutorial group where I post video lessons like this. I've also solved like top 5 toughest questions from the tutorial sheet. You can join the group. You can text me if you want to join the group, so that you get exposed to different questions. There are different questions on dimensional analysis. So I think before you go, let me give you another question. Yeah, I'm going to solve it, but I want you to pause, try to solve it, then we compare the answers. Okay, so here it comes the question. Okay, so the question is saying that show that the following you are supposed to write the equation. The following equation, show that the following equation is dimensionally correct. This equation of linear motion on kinematics. Okay, so you can pause the video. In fact, you should pause. Try it at least. Try. Get stuck somewhere, then you continue playing it. We compare the answers. Okay, so pause it. Okay, so I'm sure by now you've tried it. So let me also solve it. Okay, so this S is representing displacement. Okay, S is representing displacement. So displacement is measured in meters. Okay, meters. These are the SI unit, and then U is representing the the velocity. So velocity is equal to meters. If you want, you can say per second or just meters with the negative s there when this one goes there on the numerator. Okay, so this is u. This u is just initial velocity u. V represents final velocity. Don't get confused. U, initial velocity. They are all velocities. Okay, so t representing time measured in seconds. Okay, acceleration measured in the SI unit is meters per second squared. So we are going to have it is same as having ms raised to the power negative 2 like this. Okay, and then now here you have t, like I've said that t it is in seconds, right? Okay, so let's write in the dimensions now. Dimensions, remember it's dimensional analysis. Show the dimensions. Always remember this. I've showed you the mnemonic. Okay, so now let us replace where this is. I'll put m. In fact, I'll put the s. I'll put the dimensions for meters. Meters it's length, right? Here I'll put meters length. There t raised. You know how to do this, right? I'm just coming up with the dimensions. So what else? T time. Still, it's going to be t. And acceleration, we're going to have length t raised to the power negative 2. Okay, seconds, meters, right? And then still at, it is still going to be like this. Okay, so now we have the dimensions. Okay, now let us replace the dimensions in the quantities that we have. Okay, if you want, you can pause again. You can try. Maybe you got stuck on the dimensions. You can pause the video and try again, and we compare the final answers. So let me replace them. I'll say, what this is, I'll put the L equal to where I have the U. I'll put the dimensions. If you want, you don't have to wrap them in square, but it's just a standard way of representing. Okay, raised to the power negative 1, and then plus 1 over 2, acceleration there. I'll put L, okay, like this. In t squared, remember there's a t. This t is just showing when the t is not raised to any exponent. So what you're going to do is that you're going to replace where there is a t with this dimension. Don't forget the exponent. This is where most of the students make mistakes. If let's say here you had like t squared, you should have multiplied the t 2 times the exponent that you add here. In our case, there's just power 1a. So it's like you're having 2 times power 1. It is going to be 2. Okay. So you have we have something like this. Okay. So remember, we need to end up with both sides having only one dimension, meaning that this side we have to simplify until we end up with a dimension for length. Okay, so first this part we can't simplify any further, right? So you're just going to write like this. So as I said, the constants don't cause any effect. So when you look at what we have here, we have t times t, same basis, right? I'm multiplying. What do? You add the exponents. What are the exponents? You have negative 2 and positive 2. This will give you 0, meaning that so you are going to end up with a t to the power of what? 0. So let me just write it here. So first you have the L. This hasn't gone anywhere. You have the L here, and then you have. And then you also have a t raised to the power of 0. And here, not to forget, I've just forgotten one thing. As you can see, this is the velocity, right? The velocity, it is L. I've just written for the velocity. I've forgotten to include the dimension for time. So here you include the dimension for time. You also include, I think, mistakes are very normal, guys. Mistakes are very normal as long as you are able to correct them. The goal is to be able to notice the mistake and you correct them. Okay, so I think let me just rewrite this now properly. So I'm going to have this t is representing time, and then these are representing for u, the velocity. Okay, the initial velocity in specific. So 1 over 2. Remember I said that a at the moment we only have this. Okay, so after we simplify further, we have just remained with the length raised to the power of 1, and the t raised to the power of 0. Okay, let's simplify this part further. So you're going to have here you have the L. Remember you have 2. These are same bases. These two same bases are multiplying. This one is raised to the power of 1. Okay, meaning that you're going to write the base that in common, the t. Okay, you add the exponent, that is 1 plus -1. -1 plus 1, that will be 0. And meaning that you're just going to remain with 1, that is the L, right? Plus 1 over 2, 1 over 2 there, and then here you're going to have the L raised to okay, like this. Now remember that anything raised to the power of 0, it is 1. So here you can just replace 1 or just none. So let us replace 1 there. You're going to have L on this side. Here you're going to have 1. Here you're going to have L. And 1 over 2. 1 over 2. 1 over 2. Here you just like have 1. Okay. 1 times L, you're just going to get back the L. So let me just write, in fact, you're just going to remain with this and this. Okay, so let me just write now on the next page. Okay, so right now, after simplifying, we have remained with this. Okay, here I've just cancelled the 1. It's a 1, but I've just decided not to include it. So as you can see, we have same dimensions that are adding. If you want, you can just go directly and say LE and just write 1 L. You ignore the constant, you even improve. Okay, now for you guys who are overthinkers, that you'll be like, yeah, okay, now Joseph, you said that the constant don't affect. Okay, so now let's consider the constants. Okay, if you want, you shouldn't. In most cases, they are not considered. But even if you do, the answer will still be correct. You will still show that it is dimensionally correct. So you're now going to yes, like this 1, right? 1 over 2. 1 plus 1 over 2, it will give, I mean, you consider them to be like terms, then you add what is in front of them. So meaning that you're going to have here the length dimension, then equal to the, here you're going to get 1 plus 1 over 2, 3 over 2, right? And then you're just going to end up with 1 dimension here. Still, you are not interested in the constants. Okay, we just want to see the dimensions being the same. So every formula that we use is dimensionally correct. For a scientist, every scientist who ever discovered the formula, for it to be in books, they had to sit down and do the same dimensional analysis that you are doing right now to accept it, to be widely accepted. So this is all you need to know. Okay, if you want, you can just ignore this. Okay, you can just end here, even say, your lecturer even know. Even lecturers will be seeing your work, they will know that, okay, this guy's understood what he or she is doing. Okay, so that's how you do it. I think this is all you need to know. I think I've even taught more than enough. I know the video is quite long, but it is worth it because you've learned something that probably you didn't know. And have a very nice day. And don't forget to join my tutorial group where you have access to videos like this in 4 courses: biology, chemistry, physics, and math, as I expose you to questions like this. It's questions that are quite challenging, but I'll try to break them down for you and simplify them. And have a very nice day, and I hope that you have understood. Don't forget to subscribe to the YouTube channel. Of course, make sure that you subscribe. Make sure you also like the video, and I repeat, make sure you share this video to your friends as well. Make sure that your friends also know what I've just shared in this video, because it's very important, and it's very rare to find the explanation that are in this video, because even me, I really struggle to find this knowledge. So have a very nice day once again, and goodbye.